Hey, we'll start in a minute. But I think what I'm going to do, I'm going to not show you the old way that it was done. I'm going to show you the new way, the way I like to do it. So we'll start in about 5 minutes. I'm going to go get a drink. So I'll be right back. All right, let's start this in a minute. Oh, I gotta check the stream. I got background. All right, test 1, 2, 3. Oh, yeah, got it. Forgot to wash my hands. Be right back. All right, so what I'm going to do, I'm going to keep going back to this problem. Let's go ahead and do a copy out these two parameters. So here, this is what I mean. Go over here and okay. So let's just go to the very bottom here, and we're going to put this equation right here. So you got a head gain, right? So let's look at each of these terms so that we get a clear understanding of what's happening. This one, loss in the pipe. It could be plural, it could be pipes. This is the minor loss. This is the pump. And this is the height difference between the two bodies of water. So with that in mind, let's take a look at, let's focus on the pump for a second. And let's pick this pump. Here we go. I'm going to copy. I'm going to put it right there, say maybe. Now here's the thing about this. Let's look at the units over here. Okay, the units. Okay, hit the escape. Now I figured out how to do that finally. Units are feet. That's what we have right here. Now, we don't know this. Let's say this is going to be 400 feet. Well, maybe we'll stick. Yeah, we'll make it 400 feet. So the two, go back down here. So here's our picture. Maybe I can stick it right there. So instead of it being how about we say 350 feet? So that means that this is going to be 350 right here. Oh shoot, if you don't mind, I may cut the volume off and get this. Maybe my doctor. Okay, that was my doctor. Okay, but let's get back to this. Um, I'm gonna I'm gonna let this stream go a little longer than normal so I can finish up this. Right now, looking at the stream things and okay. So we've worked this problem out. We've worked out these values, this value. We figured all this out, and we're going to say this is 350 feet. So what pump do I need? Let's say I'm given these three choices: a 6-inch diameter, a 7-inch diameter, and an 8-inch diameter. So let's say we pick the 7-inch diameter. And let's say, just logically, what is the most foot ahead? I got to turn off the echo of this thing. Okay, what is the most pressure it can give me as far as foot of water? That's about 250. That's about 275. This is maybe 260. So maybe that's about 260. So the 6-inch diameter, the most head gain it can get is 260. So if you look at that, 260 minus 350, that's a minus number. So already this 6-inch diameter pump, this is a 6-inch diameter. So it could have like so essentially it could be a pipe could come in here, flow could come out here, and out the water would come this way. So it's the internal diameter of the rotor in there. It's not the diameter of the pipe. So the 6-inch diameter pump just simply doesn't have enough head to make it. So let's take this 7-inch diameter and get the highest pressure it can supply in feet. So this is about 350. This is about 375. So it can push up there about 375. Okay, so the most it can get 375. So at least 375, at least it can give you at least 25 extra foot ahead. So what we're going to do right now is we're going to go with that pump. And the question is, how do we put it in? Because here's what happens. This is, I'm sorry, it's a 7-inch diameter pump. It may start at 375, but as the flow rate gets out there, it starts dropping. Eventually, it'll drop to the point where it cannot supply more than 350 at that point. So if there were no losses, meaning that these terms here didn't exist, the best you could do is get yourself to about right here, and that's what you could get. But that's not what we have. So how do we do this? Here's the approach that I often take. I'll often take this approach. Now, here's gallons per minute, but I want to turn this into cubic feet per second because that's what my Q is going to be listed as. So I'm sitting there and looking at this and saying, how do I do this? Well, what you do is you notice this curve sort of, this curve sort of drops off like this. So a convenient model might be that the head is equal to some constant C1 minus some other constant C2 times the Q. And it looks like a Q squared. So this looks like it drops off parabolically. Turns out that C1 is easy because if you put in, so this is basically the head as a function of the flow rate. You increase this, it decreases the head. So if you put in Q is equal to 0, so in other words, what is the head when Q is equal to 0? Equal to C1. Well, we just determined that that's 375. So that means the head as a function of Q is equal to 375 minus the second term. Now here's where you're going to get an approximation. You know, I don't know what the best approach to do this is. I think that often people do this iteratively, but from my view, this is the way I like to operate this. I go in and I find this is the efficiency of the operation. So I find that if I were to draw the best efficiency for these pumps, I would say it would be along that curve. In other words, if you want to operate this pump, the best place to operate is right there. It's the most efficient point. You want to operate the 7-inch pump, you operate it right there. If you want to operate the 6-inch pump, operate it right there. That's going to be your best point. So if I look back, I'm concerned about the 7. So what I'm going to do is I'm going to look at this. And that's going to be my second operation point. So what does that mean? That means, looks like it's 180. Looks like that's about 170. And it's about 192 gallons per minute. I'm going to rely on the lovely internet. And what I'm going to do, I'm going to go in here. I'm going to say 195 GPM to cubic feet per second. Okay, I forgot 192. So 192 gives me nothing. Oh, cubic feet per second. 0.514. So I'm going to say it's about 0.514 cubic feet per second. And what do you get there? Well, if that's it's got to be 325, and that's about halfway. So I'm going to say that's around 310. So this means the head at Q is equal to 0.514 is equal to about 310. How do I put that in this equation in order to find C2? Well, what I do is I take it down. I say 310 equal 375 minus C. 0.514 squared. Take my C over to the other side. C equals to 375 minus 310 0.514 squared, which would be approximately 246. I'll say it's about 246. In these particular cases, you know, those digits 375 minus 246 q squared, where h is in feet, q in cubic feet per second. This is a very important equation here. Why? Guess what? It can be stuck directly into that equation. So here's the way we're going to do this. We take this equation again. I'm going to copy it. This time I'm going to put it right here. I'm also going to grow it a little bit. Maybe it's a little too big right there. So, you know what? Maybe I'll just drag it down here. What I'm going to do is I'm going to take that 350, that's how high I'm pumping, and I'm going to move it over to the side. I'm going to take this head gain and subtract it off and do 375 minus 246 q squared. Now, I want you to take a look here. This is a very important thing to consider. Here's what I'm going to do. There's my equation. What do you find interesting about that? What you find interesting is that it's a very well behaved equation. So reality, or a real problem here, is simpler than the textbook. Look at that real close. So let's continue to work this problem. Let's find out what the flow rate here is. The fan kicked way up on the computer, so I don't know. So first of all, 375 can be knocked out of that. And so, yeah, 500 over 75. Now guess what I'm going to do? I'm going to say q squared over area squared. Wait, I'll do this for 2g area squared. Why? Well, q is equal to AV. And if I've got this, let's look real close here. Let me get my fingers right. Or here, let's do it this way. Grab this part. Move it over here. And take this part. Just for space limitations, I'm going to move it up here. I'm going to put parentheses. I'm going to draw this back. And then I'm going to add 12.8. So I'm going to pause and say, let's look at this. This term right here. This term times that term. And this term right here is this 12. But you also got this, which is that. And so you've got all that. And guess what I can do here? I can take this, move it onto that side of the equation. Plus 246 q squared. And I can basically leave the 25 over here. 25 would be this, minus that, give you 25. Now I can go down one more set and take the q squared out completely out of everything. It would be 246 plus 1 over 2g area squared, which will fit, we'll put that in a minute, 500.75 plus 12.8, and that's still equal to 25. Now, I guess I'll address the area after I combine terms. So I get Q is equal to, here we go, square root of 25 over 246 plus 1 times 2 the area squared. I'm sorry, I forgot the F right here. 500F over 0.75, that's the diameter, 12.8. And let's stare at that a minute, and what we'll discover is there's nothing really else left there. So let me go ahead and address the area, and I'll rewrite this thing. The area is pi r squared was 0.75. If I square it, put it by 4, I end up with that number. Since we're actually interested in solving the problem, .44179. 0.44179. Now, if we look at the g times a squared, it would be 32.2 times 0.44179 squared. I get, okay, so let's see. Let's do this. Huh? No. 628.46. 628. Whoa, whoa. 6.28. So with that in mind, here's what I'll do. I like the copy thing. Okay, so what I'm gonna do, so what do? I have an equation. If I've given F, I can find Q. How do I take place in order to sweep through this? Here's what I'll do. I'll say 1, guess an F. I'll say 0.1 to start with. A 0.01. How about that? 0.01. and 2. Find the Q from that. And 3. Find the Reynolds number equal to rho velocity diameter over mu, which is 1.94 times, okay, what is this? Okay, remember here, V is equal to Q divided by A. And now, take the Q divided by the A, which was this, 0.44179. And then the diameter, which was 0.75. And then water is 2.34 e to the minus 5. And then from and E over D, find F. Once I have F, I go back to 2, and then I go to 3, and then I go to 4, and then I go back and back. So I'm looping through this thing. Let's see if we can just do that in a command line inside of Octave. So here's what I'm going to try to do. Recent editor files. Here's our pump problem, right? Let me just see if maybe I could just do that. Here, I'll do a new one. So F is equal to 0.1. Here, 0.1. And then I'll say Q is equal to, and what I'll do is I'll do a loop. I'll do 10 iterations for I equal 1 to 10. I'm going to do 10 loops here. Q is equal to, now I can't read that, so I've got to somehow shrink this down. Square root of 25 divided by those brackets, but underneath there you're going to have 246 plus 1 divided by 2 divided by 6.2846 times, close bracket, open bracket. So I'm going to take the first number of the 12, well, I'll take the first one. 500 times F divided by 0.75 plus 12.8. So I got a Q, right? And then what I'm going to do is find the Reynolds number is equal to Reynolds number is equal to 1.94 times Q divided by 0.4417 9 times 0.75 divided by 2.34 e to the minus 5. Okay. After I got my Reynolds number, what do I do? First, let's look back at what he wanted for his E over D. He said his E over D was 0. I'm going to go ahead and use that. It's a little bit off in this equation, but that's okay. I'm going to say E over D about equal to 0. Okay. So I'm going to go back to this other one, and I'm going to go in here and try to find that equation. Equation sits, it's one of those two, so I'm going to take this one. This one is a replacement for the movie diagram. Copy, go back over here, and then I'll say that. Then what I'll say is end to end for. I don't remember. Then what I'm going to do, I'm going to do f print f. First, I'm going to print %f, %f, and then %f. Line. So first thing I'm going to do is present the F, Reynolds number, and then the Q. If I save this thing, what I got, that. There's a couple ways you can do it. You can just do a run. Unfortunately, all the output probably got mad. Oh. Oh. There you go. Oh, I don't have E over D. E over D equal to 0. Let's just do that. I don't know if the... Okay, what you find out, the F is pretty converges like the second run. And then the Reynolds number pretty much converges. And this is the flow rate. So it ends up that it's a 0.317 cubic feet per second. So it turns out that Q is about, okay, we forgot, 0.317 cubic feet per second. The velocity is equal to the Q divided by the area, or 0.317 over 0.44179, which would be, I tell you what, let's do this. Go ahead and calculate the velocity. Velocity is equal to Q divided by, I forgot to put the equal. Q divided by, there it is. Let's run that. That'll tell me my, oops, what happened here? Oh. Velocity is about 0.718 feet per second. So what would happen now if I chose the other pump? Well, of course I'd get more flow rate, but I would have to put in the other pump curve and work that out. But I think at this point, I don't want to confuse the issue. So this is, in a nutshell, how you can, size a pump. Let me spend a few minutes and see if I can get you. Okay. Oh, okay. This is a unique piece of software. which actually has pump curves in it, and it's so what it actually does is models okay, it turns out they basically put this in here, so you can download this yourself, and it's got the ability to put a pump, source, tank, a bunch of pipes in here, and draw out a network map. It was built specifically for water supplies, in other words, city water supplies. It's basically open source, and the EPA up, I think, in Cincinnati, basically funded most of it, and still somewhat in charge of it. So it's a basically modeling drinking water distribution system. So you can actually use this, and it works very, very well. And here's the, let me see if I can find this. Oh, here we go. So let's see if I can go in here. Let's see. Well, set up so it's a little bit harder to see. So what you can actually do is put a backdrop of where your main supply pipes are across actually a GPS thing, and it makes it so you put it as a backdrop file, and you can use CAD and GIS systems to do that. What I was looking for is the pump thing. Finding an object, working with objects, types of objects. You got junction, reservoir, tank, pumps. So it's possible that they put the pumps in here, description of the pumps, but they may not. Oh, here we go. This is exactly what I was looking for. What you see here is a particular pump, and notice what he's got there. His head is 200 feet. His flow rate is gallons per minute. So what he has here is a 0.000138 times the flow in gallons per minute squared. So the default method of calculating the pump curve inside this code is a constant minus another constant times the flow rate squared. Now he basically wants gallons per minute here. So what you do is you put 1 point, the flow, in the head, and from that he'll basically back out all your parameters that make it quadratic like that. So you can mess around with this, or you can calculate your own equation and put it in here, or you can put point or a couple points here, and essentially this is where this pump curve can be put into this code. So it's a very nice setup, and it's also got the ability to turn it on and off flow rates at different time patterns. There's a lot of flexibility in this thing. So if you end up going to work for a city engineer or some type of civil engineering thing, this is a good code to kind of as a starting spot. It works very, very well. So I guess I'm a little reluctant to download it, but maybe I'll do that later. So with that, what I want to do is apologize first about not making it. Second thing is I'll be there on Monday and Tuesday to answer any questions, tell you a little bit about things. This weekend I'll send out adjustments of the grade based upon the new thing we've learned, and we'll just go from there.